Recall that the moment induced by two forces, which are equal in magnitude, opposite in direction, and not on the same line of action, creates the tendency to rotate. And this tendency to rotate is equal to the moment of one force about the point of action of the other force. And this fits well with a definition of R cross with F. What I mean by this is in two-dimensional problems where it's usually not too difficult to find the perpendicular distance between the two forces, then go ahead and multiply the magnitude of one of the forces, in this case either FA or FB, with the perpendicular distance between the two forces, FA times D or FB times D, where of course FA and FB are equal in magnitude. If you prefer to work in Cartesian vector form, which is usually the preferred method in three-dimensional problems, then go ahead and use R cross with F, and you simply choose your F. I'd like to choose force FA. That means this R vector will have to be from the point of application of the other force. Let's call this point point B and this point point A. So if you choose force FA, then this R vector simply has to be from the point of application of the other force, which is point B, to the point of application of your chosen force, which in this case is point A. That means if you had chosen force FB, then this R would simply go from point A to point B. I hope this is clear that two forces which are equal in magnitude and opposite in direction and not on the same line of action, they create a pure moment, and its effect is to cause the tendency to rotate. Well, when you're working with a screwdriver, the force that is exerted by your hand on the screwdriver is a very good example of pure moment caused by two forces, which are of course equal in magnitude, opposite in direction, and not on the same line of action. If we're interested in forcing this nail into the wall to the right, then the tendency to rotate caused by these two forces would be in the clockwise direction if you're looking directly at the nail. The next time that you have a screwdriver in hand, I'd like you to remember that you are applying a pure moment, which means if you are interested in forcing this nail into the wall to the right, then the tendency to rotate is in the clockwise direction, of course, caused by two forces which are equal in magnitude, opposite in direction, and they are not on the same line of action. Another name for pure moment is couple. Another name for couple is torque. These three words mean the same thing, and I will use them interchangeably. Remember that pure moment, couple, and torque, they are vector quantities, which means they have magnitude and they have a sense of direction. Well, I'd like to show you a very simple experiment that involves a horizontal beam, and the objective of this experiment is to simply find a way to balance this horizontal beam when a 5-pound force is applied 20 inches to the left of the pivot point. Well, of course, there are many ways to balance this beam. I'll show you several, but a very obvious way is to apply a 5-pound force 20 inches, of course, to the right of the beam. This will, of course, balance the beam. How about if we decrease the force by a factor of 2? Well, I hope your gut feeling says that you will need to place that force by 40 inches to the right of the pivot point. That means if you decrease your force by a factor of 2, you will need to increase your distance from the pivot point by that same factor. Well, how about if we increase the force by a factor of 2? Then I hope your gut feeling says that we will need to get closer to the pivot point, and that means we will need to decrease that distance by that same factor. So from 5 pounds, it's increased to 10 pounds by a factor of 2. The distance is then decreased by that same factor from 20 inches to 10 inches. So what's the key here? I think we all get the picture that we need to counterbalance the beam's tendency to rotate. So why don't we examine this? The beam's tendency to rotate. If we apply a 5-pound force, which is 20 inches to the left of the pivot point, then the tendency to rotate is in the counterclockwise direction. And the quantity is, of course, just 20 inches times 5 pounds, which is equal to 100 inch-pounds. So the key here is to make sure that we have a counterbalancing moment, which is in the clockwise direction, and the magnitude will have to be 100 inch-pounds to counterbalance this tendency to rotate. Even if we decrease the force by a factor of 2, this will not affect the counterbalancing moment needed to balance the beam. We will still need 100 inch-pounds. 40 inches times 2.5 pounds is indeed 100 inch-pounds. If we were to increase the force by a factor of 2 still, we will still need 100 inch-pounds counterbalancing moment in the clockwise direction to balance the beam. Well, the question then is this the only way to balance the beam? How about if we balance the beam using pure moment? If you recall the conclusion that we had concluded in the previous lecture of pure moment induced by two forces, of course, equal in magnitude, opposite in direction, and non-collinear, is the same about every point on the body. Its effect is to cause the tendency to rotate. So let's take a look at our horizontal beam one more time. And our only constraint to balance this beam is that we need a counterbalancing moment in the clockwise direction, and the magnitude has to be equal to 100 inch-pounds. Well, does that mean that when we apply this pure moment to balance this beam, that it needs to be placed 20 inches to the right of the pivot point? Well, not necessarily so, because according to the conclusion in the previous lecture, that pure moment induced by two forces is the same about every point. Well, we just want to make sure that when we apply two forces, when we multiply the magnitude of one of these forces by the perpendicular distance between them, that we better make sure it's equal to 100 inch-pounds, because this is the necessary counterbalancing moment that is needed to balance the beam. How about if the length of the entire beam is equal to 100 inches? Well, that means if we apply a force at each end of the beam, then the magnitude of these forces would just have to be 1 pound, because 100 inches times 1 pound is indeed 100 inch-pounds, and the tendency to rotate is clockwise, which is needed to balance the beam. What is the conclusion then of all this? To balance this beam, we don't necessarily need to apply a force some distance away to the right of the pivot point. All we need is to make sure that there is a counterbalancing moment that has a magnitude of 100 inch-pounds in the clockwise direction. So to balance this beam, we could apply a pure moment and place it anywhere that we'd like, even at the top of this pivot point. Just make sure that it is equal to 100 inch-pounds and it is in the clockwise direction, because that is what is needed to balance this beam.